Today we're going to talk about the class equation. In the last lecture we talked about conjugacy and conjugacy classes. Remember, a conjugacy class is the collection of all elements conjugate to a particular element, or the collection of all elements conjugate to each other. And we said that elements that are conjugate to each other are somehow similar to one another. So we saw the group of symmetries of the square, and we saw that the rotations by pi by 2 this way or that way were conjugate to each other, whereas rotations by pi were just conjugate to rotations by pi. And then we saw that reflections in these two lines were conjugate and reflections in the diagonals were conjugate, and that they were somehow reflections in a vertical kind of different from a reflection in a diagonal, but reflection in either of the diagonals is kind of similar. So what we're going to do today is look at how just looking at those conjugacy classes and just looking at the size of the conjugacy classes can tell us an awful lot about the group in a way that at first sight looks a little bit stupid. So this is section 6.2, the class equation. So all we're going to do is write down an equation that consists of adding up each conjugacy class size, and of course the total of all the conjugacy class sizes must be the size of the group. So for example, in D4, the conjugacy class sizes were we had E that was in a conjugacy class all by itself, right? And then we had A and A cubed. We had A squared all by itself, and then we had the reflections B1 and B3, and we had the reflections B2 and B4. So we've got this size 1, 2, 1, 2, 2. So all we're going to do is write them down. The total is 8, and so we're just going to write down the sum of all these things, and we usually write them in ascending order. 1 plus 1 plus 2 plus 2 plus 2 equals 8, yes. We know it equals 8, so the point is that writing it out like this actually tells us something interesting. How is that possible? Well, it does, and we'll get onto that in a little bit. But the first thing to note is that actually we can often work out what this equation is without actually having to work out what all the conjugacy classes are, just by narrowing it down according to what these numbers have to be. Because if each of these numbers is the size of a conjugacy class, we've seen that the size of a conjugacy class has to divide the total number of elements. So all of these numbers had to be factors of 8. So we couldn't have you know, 1 plus 3 plus 4 equals 8. That is not a valid class equation because 3 doesn't divide 8. So I'll make all this precise in a minute. Well, in fact now, let's just write down first of all exactly what the class equation is. Okay, so definition 6.2.1, let G be a finite group, and let's give ourselves some notation for its conjugacy classes. So let's call them C1, C2, and so on up to CK, because there can only be a finite number of them. Then the class equation for this group, the class equation for G is, you just write down the size of each conjugacy class. and you declare that it has to add up to the total number of elements in G. So you write down what these numbers are. Each of these numbers is, well, each of these things is a number, and then you say, oh, well, it adds up to the total number of elements in G, and that's what the class equation is. So let's do another example. We've kind of done D4 already, so let's try the permutations of 3 elements. That's a nice, easy one to get us going. Example 6.2.2. Okay, let's do S3, class equation for S3. So remember that the conjugacy classes consist of the sets of elements of the same cycle type. So elements are conjugate if and only if they have the same cycle type. So the first thing to do is to write down what all the different possible cycle types are. So the possible cycle types are, so when we write down the cycle type, we write down a list of numbers that consist of the length of the cycles if we write it in disjoint cycle notation. So 3, a typical cycle, let's write e.g. a typical cycle is that cycle 1, 2, 3. Then the other possibilities are that we have 2 and then 1. So a typical cycle type is just a transposition like that. And then 1, 1, 1. I mean, we could have written the last cycle as just a single element like that, right? But I'm not necessarily going to bother. And then 1, 1, 1 means that you've got 1 and 2 and 3 all as cycles by themselves, which means that that's just the identity, okay? Now, how many elements are there of this cycle type? So the number of elements of this cycle type, well, how many 3 cycles are there in S3? There are 2, right? Because there's that one in the backwards. How many transpositions are there? Oh, well, there are 3. Because the only choice you have here is which element you have left out. And how many elements of the identity are there? Well, there's only 1. So the class equation is very simple here. So the class equation is 1 plus 2 plus 3 equals 6, because we can check that the total number of elements here is indeed 6, which is what it's supposed to be. So let's just observe something about this equation. Observe that each of these numbers is a factor of 6, because each of these conjugacy classes has to be a number that divides 6. So that's perfectly fine. And my phone is ringing, and it's also time to stop this video and go on to the next one.